Number 21 here is a pretty tricky problem. I want to remind everybody that what we're trying to do in 5.8 is to recognize our integrand as the general structure of a derivative that we learned back in the first semester. And so what I think we're looking at right here, guys, would have something to do with the derivative of inverse secant. And if you remember, the derivative of inverse secant would be 1 over, it would have been the absolute value of u times the square root of u squared minus 1, and then times a du dx at the end of all that. That's not exactly what we're looking at, but I think close enough that we can make this fit. So here's what I think we're going to do, guys. I think we're going to let u equal, not exactly everything right here, I think we're going to let u equal x squared. Now, the reason for that is I think that's going to turn this x to the fourth. In fact, let me go up a level with this into something useful for us. If I square both sides of that equation, you're going to get u squared is equal to x to the fourth. So let me just go ahead and start doing this and see how it looks here, guys. My primary substitution then is down on the bottom. I'm going to have a radical now, and that x to the fourth right there is going to get replaced by u squared. And the square root of u squared minus 1 is something I very much wanted to have on the bottom of that fraction, because I think now I can set up my antiderivative using inverse secant. But all that was the primary substitution. We still have to worry about this x right here and this dx right here, and that's where this problem gets really tricky. Okay, so let's go ahead and differentiate both sides of this initial substitution here. Du is going to equal a 2x and a dx right here. Now, that is not what I was expecting to see right here. We need a dx right here divided by x, not a dx multiplied by 2x. So when I was just kind of tooling around with this problem, I came up with an idea that actually kind of seems to solve two problems at once. But I don't think we did anything like this before. I'm going to artificially put another factor of 2x up there in the numerator of the integrand, which I could only do if I also multiplied another 2x down on the bottom. Now, why in the world would we want to do that? Well, for starters, right here now, 2x multiplied by dx is what we have right here, so all of this can now be replaced by a du at the end of all that. And what we have still to cover now, guys, is this quantity right over here, 2x times x, which of course is going to be 2x squared. And do we know what to do with a 2x squared? Well, kind of. If we looked at this equation right here and multiplied both sides by 2, 2x squared could be replaced by a 2u. So that is going to go right here on the bottom. We'll have a 2u multiplied by the square root of u squared minus 1. So that is definitely outside the box, guys. I'm not sure that's the best or most efficient way to do that, but as I'm looking at the solutions manual, they just kind of concocted something and didn't really explain how they got it. So hopefully with what we did there, it at least makes some sense as to why it would work and that it does. Now, is this what we wanted? Pretty much. That 2 on the bottom is problematic, but remember, any constant can be factored out. So a 2 on the bottom means we're pulling out a 1/2 as a constant factor here, and then we've got 1 over u multiplied by the square root of u squared minus 1 du, and that would be the derivative of the inverse secant of u. So that's going to leave us with a 1/2 and then an inverse secant of u, and because it's an indefinite integral, we'll put a plus c at the end of all that. And all we have to do now, is go back to what I had right here, but ignore those red 2's. U was equal to x squared, so we'll have a 1/2 times the inverse secant of, and again, u was x squared, and a plus c, and that's going to be our answer there for problem number 21.